In this video, we will consider a particular class of Bayes estimators, linear Bayes estimators. In fact, it is session 1.12 of our reference book, Empirical Bayes Methods, second edition. This session is about approximate Bayes and empirical Bayes method, and this video will be about part of this session. First, we will consider point estimation, but in fact, the idea could be extended to other types of decision. And first, let me define what is approximate Bayes estimators. Approximate Bayes estimators is any point estimator divided by using the prior distribution to find a best estimator within a certain class. Okay, and here the approximation is a linear function in the following form. Okay, point 2. The delta is our decision. Now we specify the decision as a linear function. Okay, and here the situation is to make it simple, we have only one observation of x and the corresponding parameter of interest is lambda. Okay, and in this linear decision rule, we have two constants to be estimated, omega 0 and omega 1. Okay, and we will choose omega 0 and omega 1 to minimize the Bayes width. As usual, we consider point estimation and we use the quadratic loss function, which is the quadratic distance between the point estimate and the parameter, and G is the pi as usual. Then the minimization is straightforward. We differentiate with respect to omega 0 and omega 1. Then we will get the two first order conditions as written here in green color. Okay, and now here two conditions, and this condition after some algebraic manipulation it is very straightforward. Then we can get these two equality, okay, which are in terms of the conditional expectation of x conditional on lambda, okay, and yeah, conditional moment of x conditional on lambda, okay. So this is the simplification, and then we can write things in matrix form. Okay, so this is the formula which determine the optimal omega 0 and omega 1. Okay, and in this formula, we need to estimate or specify the conditional moment of x. Okay, then let's consider some concrete example. We go back to the example where x conditional distribution of x is a Poisson distribution and the parameter in the Poisson distribution is lambda. And it is straightforward. Then we know that the conditional mean of x is lambda and the conditional second moment of x is lambda square plus lambda. Then by direct substitution, we know that omega 0 and omega 1 for a given Poisson prior distribution is given by these two formula. Okay, given by these two formula. And then just like our previous example, we may assume the prior distribution of lambda follow a gamma distribution. Then it is very straightforward and algebraic exercise to find that the decision rule is in fact of this simple form, beta plus x over alpha plus 1. And it is interesting to see that in fact in this special case, the approximate Bayes rule is exactly the Bayes rule, okay, in orange color here. But surely don't think that this general conclusion will hold in general, okay? Because in general it may not equal to each other. Then the last remark is this. The linear Bayes estimator are easily adapted to empirical Bayes estimation. For example, in star, the matrix equation, we can estimate the moments of x, okay, the moments of x by the observation, right? Because it is a integration over lambda, so it is something like a unconditional moment of x, okay, unconditional moment of x. So we can use the repeated observation, just like what I talked about in session 1.8, empirical Bayes approach. We use x observation to estimate the marginal distribution or the moment in the marginal distribution.